Next, let us count tuples with non-repeating entries. And non-repeating we can interpret in several different ways and count each of them. So let's define some of these notations. A tuple A1 and so on AK of any kind of objects is said to be injective if A1 and so on AK are distinct, so no two of its entries are equal. This is the maximum notion of non-repeating. This is the best you can ask for. Next, Smirnov if no two consecutive entries of the tuple are equal. So if it satisfies AI is not equal to AI plus 1 for each I. So an entry can repeat, but only after a wait. It cannot repeat immediately. And Smirnov, that's the name of somebody who has studied this, but people also call them Carlitz or non-stuttering. Non-stuttering is just a way to think of this condition. And finally, 6 Smirnov, which is short for cyclically Smirnov, if it satisfies, first of all, the Smirnov condition, and also AK is not equal to A1. So this is saying no two consecutive entries are equal, and this is saying no two consecutive entries are equal if you write the tuple on a circle or on a band. So the last entry and the first entry are also considered to be consecutive. So how do we count those things? Well, just for the sake of, just to make sure, here are some examples. The tuple 512 is injective, therefore 6 Smirnov, and therefore Smirnov. Every injective tuple is 6 Smirnov, and every 6 Smirnov tuple is Smirnov. Okay, I should probably acquire that case, not 0 here. Otherwise, it's not clear what the first and last entry are when there's no entries to begin with. The tuple 212 is not injective and not 6 Smirnov, but it is Smirnov. Next, the tuple 2121 is 6 Smirnov, thus Smirnov, but it is not injective. And finally, the tuple 221 is not Smirnov, therefore not 6 Smirnov, and therefore not injective. So this is the strongest requirement. This is the middle. This is the middle one, and this is the weakest. So let's count them. Let n and k be non-negative integer. Let A be an n-element set. First, how many injective k tuples are there with elements in k? Secondly, how many Smirnov k tuples are there? And finally, how many cyclically Smirnov are there? So 6 Smirnov. Truth be told, I'm just abbreviating this so this fits on certain lines, because I would otherwise have very long formulas that wouldn't fit on the page. And here it helps to assume that k is bigger than 0. K0 is sort of an annoying exception. So how do we approach it? For part A, so this is just asking how many k tuples have no two equal entries. So you can think of a tuple as a map from the set k to A. So first of all, bracket k will mean this k element set. Now a k tuple A1, A2, and so on, AK in A to the k is more or less the same as a map from k to A. Why? Because you can take the map that sends 1 to A1, 2 to A2, and so on, k to AK. Clearly, the map carries the same information as the tuple. And furthermore, the k tuple here is injective if and only if the corresponding map is injective. And that's why we call them injective to begin with. So, formally speaking, this means that we have a bijection between the injective maps from k to A and the injective k tuples in A to the k. And this map, so this bijection sends a map to its list of values. So the bijection principle yields that the number of injective maps equals the number of injective tuples. But the left-hand side, we know, we have a formula for it here, with injective maps between two finite sets. So we also know the right-hand side. So the right-hand side equals the left-hand side. And this is, because A is an n-element set, this is n times n minus 1 times n minus 2 times and so on, times n minus k plus 1 by the preceding theorem, since this is a k-element set and this is an n-element set. So part A is solved. Now, what about part B? What about Smirnov k-tuples? Of course, the number will be bigger because it's a weaker requirement. So here, it doesn't really help to reduce it to maps. Instead, we're going to just construct this Smirnov k-tuples. So we can construct a Smirnov k-tuple by the following method. First, choose its first entry, A1. How many choices do we have? A1 has to be in A, so we have n choices here. A has n elements. Next, choose A2. Now this also has to be in A, but it furthermore has to be distinct from A1 because it's Smirnov. A2, and if A2 was equal to A1, you would have two consecutive entries being equal. So we have n minus 1 choices here. Next, we choose A3. And A3 has to be distinct from A2 for the same reason, but it can be equal to A1 if it wants. So again, we have n minus 1 choices here. And this argument just goes on and on until we have chosen all the entries. So and so on until we have chosen all k entries. So the total number of choices, and therefore the total number of Smirnov k-tuples, is, we multiply this by the dependent product rule. N times n minus 1 times n minus 1 times and so on times n minus 1. And how many n minus 1s? K minus 1 many. So n times n minus 1 to the k minus 1. That's the answer for part B. Part C is the trickiest one. It's, if you try to approach it in the same way as here, you run into a problem, because you can begin like you do here, but in the end, when you're choosing a k, you need it to be distinct both from the preceding one, from a k minus 1, but also from A1, because the last entry has to differ from the first entry. And there you don't know how many choices you have, because if a k minus 1 is distinct from A1, you have n minus 2 choices. Whereas if they're equal, you have n minus 1 choices. And you don't know in advance whether they will be equal or distinct. So if you draw if you look at this as a path diagram, you will actually see that different paths have different numbers written on them. So this kind of dependent product argument no longer works. And we have to be a bit more systematic. So forget that we fixed k. We no longer consider it as fixed. Instead, for each positive integer k, we let C of nk denote the number of 6 Smirnov words, k-tuples. Combinatorialists like to denote tuples as words. It's just a synonym for tuple. I don't know why, but since I'm working in that field, I often misspeak. So the number of 6 Smirnov k-tuples, we just give it a name. So we need to compute C of nk. First of all, C of n1 is 0. This is because there are no 6 Smirnov 1 tuples. In fact, if a 1 tuple was 6 Smirnov, its last entry would be different from its first entry. But it has only one entry, so its last entry must be equal to the first entry. So C of n1 is 0. Now, assume that k is bigger than 1. we shall only consider tuples in A to so with entries in A henceforth in this solution. So this means that we can avoid writing this thing. We can just say the number of 6 Smirnov K tuples. We don't need to say that they're with entries in A because we already assumed that. Now we say that so a non-sick Smirnov tuple shall mean a Smirnov tuple that is not a 6 Smirnov tuple. So in other words, its last entry equals its first entry. So for 6 Smirnov, its last entry has to be distinct from its first entry. Now we require the opposite. We require them to be equal. Then I claim that the number of non-6 Smirnov K tuples equals the number of 6 Smirnov K minus 1 tuples. Why is that? Well, how do we prove that two numbers of things are equal? You construct a bijection between the two things. At least this is the most obvious idea to do, how to do it. So if A1 and so on, AK is a non-sick Smirnov K tuple, then AK must be A1 because it's non-sick. That's what non-sick means. So basically the last entry is unnecessary. It's just a repetition of the first entry. So if you throw the last entry away, this is a Smirnov K minus 1 tuple because, of course, the fact that consecutive entries here are different, it's clear because there are consecutive entries here as well, and therefore also different. However, we can do better. It's a 6 Smirnov K minus 1 tuple. Why? So why is AK minus 1 different from A1? Well, because this tuple is Smirnov, AK minus 1 is different from AK. Because AK minus 1 and AK are consecutive. But AK is equal to A1. So this one is a 6 Smirnov K minus 1 tuple. Thus, we find a map from non-6 Smirnov K tuples to 6 Smirnov K minus 1 tuples. And what this map does, it cuts away the last entry. Conversely, if you have a 6 Smirnov K minus 1 tuple, then if you just repeat the first entry at the end, so you reinsert the first entry at the end, the claim is that this is a non-sick Smirnov K tuple. I'll let you think about it, it's pretty easy. Thus, we find a map in the opposite direction. And what this map does is it reinserts the first entry at the end, without removing it, of course. These two maps are mutually inverse, check it. Thus, they are bijections. Hence, the bijection principle yields exactly what we wanted to prove here. Okay, and this number is C of nk minus 1 because we defined C of nk minus 1, we defined it this way. So we wanted to find this number of 6 Smirnov K tuples. Instead, we have found the number of non-6 Smirnov K tuples. Looks like a detour, but actually it's a useful detour. It's a detour that takes us to where we want to go. So now C of nk is the number of 6 Smirnov K tuples. And this, by the difference rule, it's the number of Smirnov K tuples minus the number of non-6 Smirnov K tuples. Because what is a 6 Smirnov tuple? It's a Smirnov tuple that's not a non-6 Smirnov tuple. So this is a typical case of how the difference rule comes useful. So instead of counting the things you want to count, the things that satisfy some condition, you count the things that do not satisfy that condition, and you subtract them from the total number of things. Okay, this number, you know, this is n times n minus 1 to the k minus 1 by part B of the exercise. And this, as you've just seen, this is c and k minus 1. All right, so instead of a direct answer, we've gotten a recursion. We know how to compute c of n k using c of n k minus 1. So this is a recursion for our numbers, c of n k. It's already a very useful thing. If you want to compute these things on a computer without actually brute forcing your way through all the possible tuples, this recursion is great. But let's try and find an explicit formula. Well, how do we do it? We plug it back into itself. So here is what the recursion says. But c of nk minus 1, we also use the recursion to simplify this. Of course, you have to replace k minus 1 by k minus 2 now. So you get this here. Okay, now you have c of nk minus 2. So you can plug this recursive formula for it, and then you get this here. All right, and so on. You can keep doing this until you go down to c of n1. So here is how it looks in the end. And c of n1, as you know, is 0 because there is no 1 tuple, that's 6 Smirnov. So this is not something that looks like an explicit formula. This is an ugly expression with nested parentheses. Well, but it's a difference, so you know what happens when you expand it. So an odd number of minuses stays a minus, an even number of minuses becomes a plus. So what you get here is a plus minus, and what you get in front of this n times n minus 1 to the 1 is minus 1 to the k. Okay, now this is still ugly, but you should be seeing something. This is a geometric series already, or rather a sum of a finite geometric sequence. And straightforward computations using the geometric sum formula finally let you find this. And if you don't want to write up these ugly computations, you can cheat. You can just claim this formula and prove it by induction using the recursion. This is often easier than actually finding it. So if you're on a Putnam and you're time constrained, which is really saying the same thing twice, you should probably do this on some scratch paper, and then on the final in your actual write-up, you should throw this stuff away. Just don't even start writing it. You should really just state this formula and explain how to prove it by induction using this recursion. All right, this is the number of 6. So this is the number of 6 Smirnov k tuples. And by the way, in a sense, this kind of indirect argument is predetermined when you see this minus 1 to the k. You couldn't have gotten this formula in any easier way. You couldn't have avoided going recursively and doing all these things, because if you're just counting using things like the sum rule, the product rule, you would never get a minus 1 to the k. You would get things that are obviously positive. If you use the difference rule, you will get things that have either a plus or a minus, but a predictable one. Whereas this is a minus 1 to the k. Really, the only way to get it is indirectly, like here. So this is probably the simplest solution we have to this problem.